My name is Xin Wei. Welcome to our session, Modeling Inspiration, where innovative approaches meet process data to inform learning. Always on the frontier of innovation, IES recently invested in 3 studies that use process data to inform education sciences and improve outcomes for all learners. Process data record the clicks, entries, and timestamps during examinees' interaction with the digital assessment. This revolutionary new data provided researchers with exciting opportunities to delve into examinees' cognitive and problem-solving processes. In our session, researchers from SRI, UIUC, Georgia State, AIR, ETS will present our latest findings from these 3 IES-funded projects. The first presentation is Math Test-Taking Behavior of Students with Learning Disabilities, a Natural Language Processing Approach. The National Assessment of Educational Progress Math Assessment data shows achievement gaps between students with and without disabilities have steadily widened over the past decade, with the share of students with disabilities meeting proficiency declining over time. The newly released NAEP long-term trend data indicate that the pandemic hurt students with disabilities the most in math because there was a more considerable drop in their math scores from 2020 to 2022 among students with disabilities than among their peers without disabilities. There is an urgent need to improve their math skills and close the achievement gap. Previous research found that test-taking behavior is highly relevant to concurrent and future academic performance, attention, behavior problems, and real-life outcomes. Students with disabilities face many math learning challenges and rarely uses effective test-taking strategies. These strategies include reading the whole question and all answers before selecting the final answer, eliminating wrong choices, highlighting irrelevant information about the question, drawing math diagrams to represent relationships, and allocating time wisely. Students who master these strategies score higher than those who don't. The lack of test-taking strategies among students with learning disabilities may suppress their performance on standardized tests. NAEP process data contain rich information about students' test-taking behavior. However, it is challenging to decipher patterns from the long sequence of categorical events and the associated timestamps. Previous studies use N-gram language modeling to identify key action sequences that are associated with item correctness or group memberships. However, process data has rarely been analyzed for students with disabilities. This study is the first to use N-gram language modeling to extract the key test-taking behavior differences between students with learning disability and their gen ed peers. This study would like to answer the following questions. What key action sequences are associated with correct response on a math fraction item? Do students with learning disability and their gen ed peers differ in percent of students who perform these action sequences? Do students with learning disabilities and their gen ed peers differ in the frequency of performing these action sequences? And lastly, do students with learning disabilities and their gen ed peers differ in time spent on these action sequences? This study used restricted 2017 NAEP 8th grade process data. The process data include action sequences and associated time usage. The restricted process data also include students' response to each math item and survey questions. Our analysis started with 600 students with learning disabilities who were not granted extended time accommodation. They completed the math block in 30 minutes. Their gen ed peers include about 25,000 students who also completed the math block within 30 minutes. We did not include 930 students with learning disabilities who received extended time accommodation because their item response times were not comparable with the general education peers. We also excluded a small proportion of students who reported having no experience with digital device and put little effort in the exam. This study analyzed the process data collected from an 8th grade fraction item. This is the 8th item on the test. When students were interacting with the item, it looks like what you see on the screen. This multiple choice item asks a student to convert a percent to a fraction. On the upper corner of the screen, we see students can change background, can zoom in and zoom out, use text-to-speech, or scratchpad. In the middle part of the screen, students can choose an answer, eliminate an answer. At the bottom of the screen, a student can clear the answer. At the upper right corner, there is a next button. Student can click that icon to exit the item. Here is a list of all the possible actions students performed on this item. They include problem-solving actions that are choose an answer, clear an answer, eliminate wrong answers. The second category of actions are accessibility to use. They include scratchwork, equation editor, text-to-speech, zoom, timer, and change color. The last set of action items are navigation items. These are enter or exit items. Our analysis to aim to identify key action differences that differentiate students with learning disabilities and their general education peers. We started our analysis by decomposing the complete action sequences into small sequences up to a length of 3. We calculate the weighted frequency, TF-ISF, of each action sequence for each examinee. TF-ISF, short for term frequency, inverse sequence frequency, is a weighted frequency to measure how important an action sequence is. We next conducted a chi-square test to test which action sequences are associated with correct response. We identified 38 action sequences that predict correct response on this fraction item. Then we tested how students with learning disabilities and their general education peers are different on each of the 38 action sequences. We also provided descriptive statistics on time usage for students with learning disability and their general education peers. Here's a flow chart. We started with almost 5,000 unique action sequences and decomposed them to 760 n-grams action sequences. 38 of them showed significant relationship between math performance, and 19 of them are facilitating action sequences that associate with correct response. The rest of 19 are hindering action sequences that are associated with incorrect response. In the end, students with learning disabilities and their general education peers differed in 6 facilitating action sequences. These 18 action sequences are associated with correct response. N-gram. This N-gram analysis include unigram, bigrams, and trigrams. Unigram is 1 gram, is also a single action. Choose C action is a unigram, as we see on the screen. A bigram action sequence can be created for each possible combination of two consecutive actions. For example, choose C followed by exit item. A trigram action sequence represents 3 consecutive actions. For example, choose C, exit item, followed by enter items. These 18 action sequences are associated with incorrect responses. In the next few slides, I would like to summarize students with learning disability and general education peers, how they are different on these 6 action sequences. First, enter item, choose C, exit item is a short, efficient, and correct action sequence that is associated with correct response on this fraction item. Comparing the percentage of students who performed this action sequence between students with learning disabilities and their general education peers, we found only 19% of students with learning disability versus 45% of general education students perform this action sequence. Choose C, exit item, and enter item is the next action sequence we looked at. This is represented by students who submitted the correct answer but come back to review and check their answer before they leave the exam. This figure shows fewer students with learning disabilities reviewed and checked the answer after submission than the GE student. When we compare the frequency of 6 action sequences, we found a very interesting pattern. The top 3 action sequences are short and correct action sequences. They are enter item, choose C, exit item, choose C, exit item, enter item to do review and check the answer. The third action sequence is enter item and choose C. Students with learning disabilities perform these action sequences less often because the odds ratio were all less than 1 and significant. The bottom 3 action sequences are eliminating answer A, exit item, enter item, and clear answers. Students with learning disabilities perform these action sequences more often than their general education peers, indicating a higher degree of hesitation, uncertainty, distraction, and repetition than their gen ed peers. In terms of time spent, we find students with LD spend a longer time eliminating wrong answer than general ed peers. Students with learning disability also spend a longer time on choosing the correct answer than gen ed student. Students with learning disabilities revisit the item more quickly than their general education student. In summary, compared to general education peers, students with learning disability were less likely to decisively choose the correct answer. They were less likely to review and check the answer after submitting the correct answer. They had a higher frequency of clearing answers, eliminating answers, alternating between different answers, and revisiting the item without submitting the answer. They spend more time deciding on eliminating the wrong answer and more time getting the correct answer. Our findings have practical implications. First, these results provide behavior evidence of the struggles among students with LD when they interact with a fraction item. Fraction is the foundation of algebra, math intervention that focus on solving fraction problems for students with learning disabilities are needed. Second, we need to teach students with learning disability test-taking strategies. Students with learning disability and their general education peers revisit the item for different purposes. Students with LD revisit the incomplete item more frequently and more quickly, possibly due to lack of focus and concentration. General education students more likely to revisit the item after submitting the correct answer, possibly doing a final review and check the answers. The review and check answers strategy has been shown to improve performance. This finding suggests teachers should teach students with learning disability good test-taking strategies in addition to help them focus better. Third, we find students with learning disability may read and process information more slowly. Therefore, extended time accommodation for them is also needed. Lastly, researchers will need to use machine learning and AI logarithm to understand at what stage students got stuck and provide immediate support and tailored hints to help them address their misunderstandings. These hints and feedback will be more useful if they can build on previous taught concepts and show students how to solve the problems in steps rather than simply providing a correct answer. These digital learning and assessment systems should also include learning analytics solutions that assist educators in assessing student needs and as a result allow for timely intervention. Such digital learning and assessment systems have the potential to accelerate mass learning recovery post-pandemic, and in the long run, close the achievement gap between students with disabilities and their general education peers. Thank you for attending my presentation. I would like to acknowledge IES providing us generous support to support this research. If you have any questions, please feel free to email me.
Hi, I'm Dr. Elizabeth Teig, and I'm going to be presenting today some of our work from our IES grant on patterns of time allocation on PIAC literacy items. And specifically, I'm going to talk about time allocation patterns for low-skilled adults compared to high-skilled adults. I'd like to quickly acknowledge the team. So Dr. Britt He from Educational Testing Service and Dr. Gal Caldez from Georgia State University. So to understand low-skilled adults, 1 in 5 adults in the US, or about 19%, struggle with basic literacy skills. And many of these adults enroll in educational programs, such as adult literacy programs, or post-secondary, what we call developmental education, or support programs at 2- or 4-year institutions, where a strong emphasis is placed on assessment performance, whether that's for progress monitoring, to complete a GED, or the AccuPlacer for post-secondary. Increasingly, many of these assessments are digital, which requires adults to not only have basic reading foundational skills or cognitive skills, literacy skills, and processing skills, but also technological or computer proficiencies to be able to meet the assessment demands of the varying item types, which might require things like clicking or highlighting, or being in different types of environments like an email environment. The PIAC, which is specifically the data set that we're going to be working with, or the Program for the International Assessment of Adult Competencies, defines literacy by 6 different proficiency levels, which range anywhere from below level 1 up through level 5. And for the purposes of our presentation, the 1 in 5 statistic that I mentioned for low-skilled adults would be the below level 1 and level 1 categories. Level 4 and 5 would be considered high-skilled or high-performing. And level 2 would still be low-skilled in the sense that these adults would only be able to engage in low-level paraphrasing and low-level inferences, so they wouldn't meet sort of college and career readiness demands. The last piece that we wanted to consider is that low-skilled adult readers tend to be very heterogeneous, and this could be demographic variability, such as age, whether they're a native or non-native English speaker, their literacy skills, as well as their basic computer skills. But it also translates into what PIAC calls skills use or engagement. And so this could be how often you engage or practice reading behaviors at home, and at work, and how often you practice basic computer skills at home and at work. And at least for daily reading practices, more engagement in these has been found to be predictive of low-skilled adults' literacy performance. So our aims then were two. The first was that we wanted to use the PIAC process data set to examine patterns of time allocation. And since we're using the public PIAC files, there's only three process variables. They are time to first action, time for last action, and total time spent on a given item. And we're looking specifically at these allocation patterns on PIAC digital literacy items across three testlets by these reading proficiency levels, so lower and higher skilled adults. And then specifically within the low skilled adult group, so level 2 and below, we want to explore whether identified time allocation patterns vary by publicly available PIAC respondent background characteristics, specifically age, whether or not they're a native speaker, and then their self-reported engagement in ICT and reading skill practices at home and at work. To give a snapshot of the sample, there's 2,697 adults available, and that ranges from 843 to 957 across the three testlets. And you'll see at the bottom there, I've listed, again, level 2 and below in literacy, the percentage that would be defined as low skilled on a given testlet. If you're not as familiar with the PIAC, this is what a sample literacy item looks like. In this particular example, it's a bullet pointed list. And then on the left panel, you see what the question is asking. So what is the latest time that children should arrive at preschool? And it's asking the respondent to actually highlight in the bullet pointed list their response. Now, the literacy domain on PIAC is pretty broad. So you may see an actual paragraph, you may see a chart, you may see an email environment, and you also may see that you have to click to respond, highlight, or you could fill in a box. So it's a pretty broad domain. For the process measures, as I mentioned, the public file only has three. Time to first action is simply the time spent prior to making a first action. And this might be the time spent reading that left panel on the literacy to see what you might have to do prior to beginning the item. And so on average, this sample spent about 37.7 seconds on time to first action. Time for last action is the time spent from the last action before moving on to the next item. Typically, that would be filling in or highlighting your response and then whether or not the respondent reviewed their response. So on average, about 4.6 seconds. And then total time is just the total time spent on each item. And on average, respondents spent about a minute on each item. We also use the public background items. So just to show you how these are coded, age is in 10-year bands. Whether or not they're a native English speaker is just a yes/no category. And then they had derived indices for the reading at work and home and the ICT at work and at home. And so these were derived based on several items where respondents responded to the frequency of how often they engage in different practices. So how often they read directions, letters or emails, newspapers, magazines, or manuals at work, and then a separate index for that at home. And same thing with the ICT at work and at home, except it was things like experience with a computer, how often they use spreadsheets, how often they use Word, and how often they use the internet. Okay, so I want to spend the bulk of the time on the results. And so again, for aim 1, we were looking at time allocation patterns by those three process variables. We ran them across all three of the testlets, but for time, I'm going to put up just one testlet from each one. So this is time to first action for testlet 3. To orient you, the x-axis contains the item numbers, and there were 9 items across all of the testlets. And then the y-axis gives us the time spent in milliseconds, but as I'm talking, I'll translate that to seconds to make it a little bit more interpretable. What you'll notice is I did combine below level 1 and level 1 because there were not that many respondents available at the below level 1 category. So that's my lowest skilled group. And then the purple line, we combined level 4 and level 5 because there were fewer respondents in that group as well. and that will be considered the highest skilled group. So what you'll notice is across the 9 items, for the most part, the purple and green line, so level 4 and level 5 and level 3, spent the most amount of time before making the first action. Level 2 followed a similar pattern, but spent a little bit less time, especially for those beginning 3 items. And then my lowest skilled group spent the least amount of time across the majority of the items. And really by about halfway through the testlet around item 5, they tapered off the most. On items where there was a big difference, the lowest and highest groups had about a 30-second difference in time to first action on those given items. This is time for the last action from testlet 1. What you'll notice is this one was a little bit less interesting because in general, across the different proficiency levels, respondents weren't spending that much time after they gave their final response. So in other words, they weren't really reviewing or checking their work. They were just moving on to the next item. And we can see this because the y-axis scale is much smaller for this one. But we still see that same general pattern where my lowest skilled group is spending less amount of time than the other groups across all of the different items. And in general is about a 4-second difference between my highest group and my lowest group. And this is total time spent. And so what we see here is a similar pattern for the highest groups, level 4 and 5 and 3, and even level 2. And again, below level 1 and level 1 are spending less time across the majority of items, with the exception of the first 3 items. And in this one, it's about upwards of a 45-second difference between the highest and lowest groups on some of these items. For my second aim, we wanted to look specifically at low-skilled adults. So we reran the cluster analysis for the different time variables to see if we actually had different clusters, and we did. So we have cluster 1, about 96 adults, and cluster 2, 263 adults. And for the most part, these clusters differentiated on the amount of time spent on the process variables. So cluster 1 spent more time across all 3 of those process variables and had slightly greater proficiency overall compared to cluster 2. When we look at the actual differences in background characteristics between the 2 clusters, we don't see differences by whether or not they were native English speaker, their self-reported reading practices at home, their self-reported reading practices at work, and their self-reported ICT or computer practices at home. But we do see differences in their self-reported ICT practices or behaviors at work, such that cluster 2 reported engaging in more ICT practices at work, which may relate to the fact that they had a shorter amount of time spent. They may have across these items and may have more familiarity with technology. Alternatively, though, if we look at age, it may also be that there tends to be younger adults, so less than 24, 25 to 34, and then sort of middle-aged adults, 35 to 44, also in cluster 2. Whereas in cluster 1, we see an overrepresentation of older adults. So these results are preliminary because we want to code out and use the restricted process data to really understand more about the action sequences. But it does suggest that although level 2 would be considered a low-skilled adult, they tend to follow similar time allocation patterns as higher skilled adults in levels 3 and then 4 and 5. So there is a differentiation between level 2 and then the lowest skilled adults, level 1 and below. Level 1 and below tend to have different time allocation patterns, spending less time in general, regardless of which process metric we looked at, with the exception of some of those early testlet items on total time. And so this raises questions about whether this could be potentially fatigue. Could it be potentially that they're not understanding the demands of the task, both from a literacy perspective as well as a technology perspective, or likely some combination of all of that? And that's what we're really hoping to understand as we're able to code out more of the behavioral variables on some of these items. And then we also noted that there were 2 distinct time-related clusters within the low-skilled group that show similar demographics with the exception of age and ICT skill use. So the cluster 2 showed younger adults and more ICT practices, yet they still had slightly lower proficiency. So even though they may have been more efficient, it didn't necessarily equate to better proficiency than the cluster 1 group. So as I mentioned, future directions, we're going to be using the restricted PIAC items and coding out and expanding on behavioral variables such as action sequences, looking at specific digital functions, so whether it relates to highlighting or clicking, as well as considering the complexity of the item, how many different environments they need to use, as well as item difficulty. I'd like to acknowledge our IES grant, and thank you very much. Looking forward to any questions you might have.
Hello, my name is Juanita Hicks, and I am a senior researcher at American Institutes for Research, otherwise called AIR. Today, I will be presenting work on behalf of my team, and the title of our presentation is Deconstructing Problem-Solving Processes Using NAEP Log Data. In this presentation, I will go over a brief introduction of the study, then present 3 key topics to cover the background of process mining. Then we'll look at our data and analysis methods, then take a look at the results and discussion, followed by some of the conclusions. Problem solving is at the heart of mathematics and is fundamental to learning math. The National Council of Teachers of Mathematics identified problem solving as the #1 process standard in evaluating the way knowledge is acquired and applied. The research on mathematical problem solving has evolved considerably over the past several decades. However, there is still limited guidance on the ways we measure students' problem solving strategies. In the literature, there seems to be 2 streams of research following the evaluation of problem solving, one invasive and one less invasive. On the invasive scale, you can think about literature where EEGs or MRIs are used to observe brain activity when performing tasks. And on the less invasive stream, it's the typical think aloud procedures or observations that we normally see in our field. So because problem solving strategies and processes are so important to us in the field, we constantly look for innovative research to identify new ways to assess problem solving strategies. And this has led us to the technological advances that we see today, and also an increased research interest into processes. Because now we have information systems that collect, track, and store data about the events and actions that users use during any given process. And that allows us to focus on a more process-oriented viewpoint. And because we have these information systems, now we can explore things like event data, log data, or process data to gain insight into user processes. And this leads us to our study goal, where we want to focus on a process-oriented method to examine existing processes involved in mathematical processes, or involved in mathematical problem solving. So why is this important? Well, think back to your earlier schooling where you were reminded by your math teachers to always show your work and show step by step how you arrived at your answer. Well, the identification of the steps involved in problem solving is critical to understand, 1, what students know and can do, and 2, to devise interventions to help them make the missing or misunderstood connections that we might see in their step-by-step show your work process. Okay, so now let's talk a little bit about the background of process mining. Well, process mining is a category of techniques used to analyze operational processes with the goal of turning them into actionable insights. The main goal of process mining is to detect and explore naturally occurring processes by extracting knowledge from event logs. Therefore, process mining has found application in many domains and content areas, such as healthcare, education, business, and marketing, because these are domains where there is specific data representing available executed processes. In 2009, Baker and Yosef classified EDM methods into 5 categories. Focusing on the 5th EDM method, which is called discovery with models, This one has become increasingly popular over the years. And often the data that we work with are so numerous or unconstructed that the first step is simply to find and explore the data for any potential meaning, i.e., discover what the data are through the exploratory means. And through this lens, researchers have coined a new term called educational process mining, or EPM. EPM focuses on processes that are thought to play an important role in exploring students' learning through visual representations of process flow that might be informative for learning. So there are three main applications of process mining, but in this presentation, we're only going to cover the first one, which is process model discovery. And this is simply where we construct process models to reproduce observed behavior. The other two, conformance checking and process model extension, are models that you would run after the initial process model discovery. And while this can be a simple model because it is an exploratory model, there are some challenges which can undermine the results of this model, such as low granularity in your data, or too many distinct and various traces, or just having low quality data, missing data, or irrelevant data. Continuing with the background, it is important for process models specifically and process discovery models that event logs have an appropriate level of interpretability. If not, the resulting model may be unreliable and incomprehensible with many uninterpretable nodes and connections. And this is what it would look like in setting A, where you take your raw event logs, you do one of the three applications, and you get this unreliable, incomprehensible process model, which we call a spaghetti model, where every action, every trace, every connection is visualized for you, but you really can't tell what it means. So the goal is to have a structured process model that is clearly defined after addressing most, if not all, of the previous challenges that I mentioned before. So this is what it looks like in setting B, where you take your raw event logs and you do pre-processing. You filter, cluster, transform, or other things, and you take your pre-processed event logs, apply one of the applications, and you get a more understandable process model where there are clear connections that actually make sense for the researcher. Okay, so now we'll take a look at the data and the methods that we used in our study. So the data came from one 8th grade block from the 2017 NAEP math assessment, and we focused on one drag and drop item. There are approximately 28,000 students who took this item, and they would split them into two groups based on their item score. So about 26,000 students got this item correct, and about 1,700 got this item incorrect. And the item simply asked students to drag the color into the appropriate piece on the circle graph, where each piece of the circle graph represents a number in the table. So for example, green had 13 votes, so we would want students to take and drag green to the biggest piece of the chart. Now, because NAEP assessments allow for flexible interactions, the analysis of full processes can be difficult to interpret, and we would have the spaghetti model as I showed before. So to simplify the analyses and the processes, we use the fuzzy minor framework. And the fuzzy minor framework is an exploratory non-parametric method that abstracts rare and non-representative behaviors and focuses on events and sequences that are highly representative of the execution of the group. And all the exploratory data analyses were conducted through the BUPA-R package. We use the fuzzy minor package to do the fuzzy minor part of the work, which makes the analysis simplified, and it takes out any of the outlier cases. Okay, so now getting to some of the results. So this first slide that we're looking at takes the most common start actions and the most common end actions for each student group. So those who got the item correct and those who got the item incorrect. And the goal of process discovery is to extract a complete model and to use all the important properties of the data to learn about the actual processes that were executed in the event log. So to that end, we usually start with descriptive statistics like this one. So we see that for the incorrect and the correct group, the most common start actions for both groups of students were to correctly place the green option and the blue option, which is great because then we at least know for the most part that no matter whether students got it right or wrong, they are starting their process correctly. However, when we look at the most common end actions, there are some differences. For the students in the correct group, we see that they are correctly placing purple and red last, but we also see that for the incorrect group, they are also placing purple and red, but they are placing them incorrectly. So although both groups of students start and end with the same color combinations, we see that both groups also place these color combinations differently, which leads to them either getting the answer right or wrong. Next, to visualize the activity traces for each group, we use this trace explorer function. And basically what this does is show us the exact sequence that students used most often on this item, split up again by the correct students and the incorrect students. What we were aiming for with this analysis was to cover or target 80% of each group. And you can see for the correct students, we covered about 77% with these traces. And for the incorrect students, we covered only 42%, which means that for the incorrect students, there is a lot more variability in the traces that they use to respond to this item. So you need to visualize a lot more traces to get to the 80% coverage. But what we can tell by looking at these trace maps is that for students who answered the item correctly, we see a few different strategies. One, where they place the colors in order from biggest to smallest. Second, where they place the biggest color first, then the matching colors, then the biggest color. And then maybe a third one where they place the matching colors first and then the biggest color in the circle graph. And then finally, we developed a process map to visualize the different path processes and connections among the actions for each response group. So while the process maps do not reflect the order of activities, they do represent the most significant actions and pairwise connections for each group. So this map shows the process model or the process map for students who answered the item correctly. And what we can see here is that there is a clear segmentation between the incorrect color placement and the correct color placements. For example, at the top, you see that these are all incorrect color placements, and they are always followed by the clear button, meaning that students recognize that they have placed any color incorrectly and immediately clear their answer before they continue on with the correct sequence of color placements. Moving on, we observe the process map for incorrect students. And again, we do see a clear segmentation where there are two different processes being observed. On the bottom, you see that there is a group of actions where you have a mix of incorrect and correct actions, but then again, almost always followed by the clear button. So in this group, students either place a correct or incorrect action, but then immediately clear them before they go on to their final sequence, where it seems that they do correctly place three colors: the yellow, the green, and the blue, but incorrectly place red and purple. And this is this segment at the top. Okay, so examining all the results together shows interesting findings for both groups. And we'll start with the correct students here. So if you think back to the item where the students were asked to place the colors in the circle graph based on the table that was provided on the left. I want you all to think back which of these, we'll call them profiles, which of these response profiles did you fall into? Did you fall into the one where you place the colors from largest to smallest according to the table? Or maybe where you started with the largest color first and then the matching colors, which are blue and yellow, then the second and third? Or maybe did you start with the two largest colors, the matching colors, and the last remaining color? Basically, all of this to say is that there is more than one way to correctly answer this question, and students provided different strategies as well. For the incorrect students, there were no clear strategies for their responses, and we saw that they didn't place more than 3 colors correctly at a time, with the last 2 being incorrectly placed. Finally, while the current study does add a lot of body to the research on the utility of educational process mining, there is still a bunch of information for us to think about to make these processes better. So one is that we can make comparisons between multiple process discovery models to see if one capitalizes on something that was missed in another model. Another one is to use the conformance checking model after the process discovery model to compare actual student processes with the hypotheses from subject matter experts. And also to do this to mine the strategies for alternative correct strategies, misconceptions, slips, or things that may have not been identified by the SMEs or by us, the researchers. So that is the end of this presentation, and I will be open to any questions afterwards. Thank you very much.
Hello, everyone. Today is my great pleasure to give the presentation on understanding adults' latent problem-solving strategies with a sequential process data using a hidden Markov model approach. So this is a project that have a collaboration with the University of Washington and also Georgia State University. So digital problem solving and digital literacy skills actually have a very good definition from the OECD in 2009. So problem solving in technology-rich environment is also called PSTRE. Is it defined as ability to use digital technology communication tools and networks to acquire and evaluate information, communicate with others, and perform practical tasks. So when we design this digital problem solving and digital literacy skills, so we generally put them into 4 steps. So for example, we start from exploration and understanding, representing and formulating, planning and executing, monitoring and reflecting. And also you can see when we design our items, we put them into 3 dimensions. The task statement dimension, technology dimension, so that is including different environment. So we can see we have email, spreadsheet, and the web pages. And also we have our cognitive dimensions. In the cognitive dimensions, actually we disseminate our the whole process by different steps, like a goal setting, planning, acquiring, and making use of the information. So there are gaps in adults' digital problem-solving skills that is in an urgent need. For example, we find a strong need to provide tailored instructional supports for adults' digital problem-solving skills. And we have 64% of US adults deficient PSTRE skills, and 23% falling at the most basic level. Technology and the use of problem-solving skills are pervasive in higher education and workforce settings. But actually, there are limited research to understand the gaps in adults' PSTRE skills, especially the adults who also are struggling with basic computer literacy in addition to the literacy skills. So we want to recommend to use a sequence-based in-process data analysis. So it's a kind of a dynamic records of actions generated during the digital problem-solving skills, form a distant sequence from the respondent's input. For example, we have time-stamped actions such as mouse clicks and keystrokes. Here is a kind of example. So you can see when we collect all the data from the process, we will put them as an event and also timestamps. So based on these kinds of data format, we can have the feature-based approach, graph-based approach, and also sequence-based approach to analyze them. So feature-based approach is generally when we have this kind of action sequences and also the time sequences, we can extract the feature from them. For example, very commonly used is the number of actions. For example, we count how many actions are there and also how much time for each action the people use. And second one is a gram-based approach. Gram-based approach is starting from your action sequence, and then you will have all the grams that are adjacent to each other. For example, if we put as a unigram, so that is each action will be a kind of a element. But if we put 2 or 3 together, so we become a kind of mini sequence. So based on this kind of mini sequence, we can put them as a kind of features, and later on we can do the analysis. The last one is a sequence-based approach. Sequence-based approach actually also divided into 2 parts. The first one is observe the sequence, and the second one is a latent sequence. So the observe the sequence is what we have already seen here. So starting from start and until the next OK. So that means you confirm you want to switch to the next item. So based on this kind of observe the sequence, we can, in the previous research and the literature, we can find people generally use the sequence as a whole and to calculate the distance between the action sequences. But today we want to introduce the latent sequence-based approach. So that means based on these observe the sequence, and we want to come down and find the underlying state transition in between. So the researcher aims, the aim one is we have explored and visualized the underlying strategies and the transitions adopted by adults by high or low literacy levels want to solve the same complex digital task. The second aim is pinpoint the potential reasons of success and failure according to the typical problem-solving strategies adopted by adults at high or low literacy levels. The last aim is better understand how literacy proficiency contributes to the measurement of adults' problem-solving skills. So in our study, we use the participants like the number of participants is 1,338 adults in the PSDRE. And we have 48.4% of low literacy people. So that is when we define our PSDRE, we have 4 levels. We have below level 1, level 2, and level 3 to level 5. So that is in the literacy. So we put the below level 1 to level 2 into the low literacy level, and level 3 to level 5 into the high literacy level. And in our sample, we have 46.9% of male, and corrected people is 65.8%. And we also find in our sample, we have a 50.7% above high school level. So that is high educated people. And for the average age is 39.2 years old. And we also check for their ICT at home and ICT at work skills. And we also find the differences between the low literacy and high literacy. So the differences between the ICT at home is something like a 0.4 in between. And also ICT at work is from 1.97 to 2.23 as the high literacy. And here is a kind of sample PSDRE item when we want to present what kind of things we can find the underlying problem-solving state. So for example, in our sample study, we have the spreadsheet and email, these 2 environments. So the task is to identify a specific club member ID from the spreadsheet. So here is an example of the spreadsheet. So in this spreadsheet environment, the respondents can click in the menu part and also click on this kind of button and also switch by different places environment. But here is a kind of a single environment. So in the task, actually, the responses need to come into the spreadsheet environment and then switch into the email page. And email page, they need to send in the key information from the correspondent email and also have their ID number there. So in our environment, we can use different tools to help us to find the key information. For instance, we can use a searching, sorting, or copying and pasting. And also for the buttons here, you can see we have the menu page and menu buttons, and also the buttons on the toolbar. And the typical action sequence you can see, actually, we can start and then to spreadsheet and also type in different key information and to find it and come to the email page and email sending and then come to the next, okay, and. So for these kind of case, we find from the high literacy people and the low literacy people, when they spend their action sequences, you can see there are different distribution between their number of actions. For the high literacy people, generally they will have more action sequences around 10 to 15, this kind of actions. Here is the peak value. But coming to the low literacy people, you can find people generally use the number of actions. It's pretty high, like in only 1 or 2 actions, because there will be quite a lot of people just quickly skipping. In our study, we present our hidden Markov model. Hidden Markov model is a kind of way we need to concentrate on 2 kinds of a probability transition. So you can see from the Y1 until YT, that is observed actions. And for this kind of observed actions, we can come into the latent state. So each action can represent our latent state. So here is the B value, we'll call them as the emission probability. So that is how much your actions can represent our latent state. And within each state, actually, we also can have a transition probability. So we call them as A parameter. So you can see from the S1 to S2 to S2 to S3, or even the other way around. And you can see the different probability of the transition between each state. So here, actually, we can understand how much probability from one latent state to the other and to track the different strategy by people from different groups. So in our research design, we have a couple of steps. So we have step 1 is to fit our HMM model on the high and low literacy people by 2 groups. And then we fit our HMM model into the 4 groups. So that means we separate them into the high literacy with a correct response, high literacy with incorrect response, low literacy with correct response, and the low literacy with incorrect response. And then in the step 3, we compare the latent state and transition probabilities among the groups from step 1 and step 2, and to make the comparison between them. So here are some results we want to share. So the first results come from the transition patterns in high and low literacy levels. So you can see from our low literacy, here are 10 states, and from high literacy, we have 8 states. So low literacy people generally have more diverse strategy to solve an item and make it wrong. So you can see we have more states here. But for the high literacy people, generally people will use similar strategies to make it correct. And let's see in the detail. So for the high literacy people and low literacy people, especially in the key press, this kind of a state. And it's interesting to find high literacy people, they have 2 latent key press states, but the low literacy people only have 1. So for the high literacy people, we go deeper to see key press 1 and key press 2. And we also can find these 2 actually represent when people have the searching toolbars. So they need to type into their key information. So that is the first key press. And then we also find people after they key press into the searching to find the key information, they want to switch to the email page. So in the email page, they also key press the second time. So type into what kind of information they find. But for the low literacy people, there is no the first state of the key press. So that means that they use not quite often for this kind of tools. Even they use a search function over here, but they do not come into the key press, this kind of latent state. And the second interesting find is we find in the low literacy people group, we have this kind of cancel to end or email report, email response, this kind of a back and forth, this kind of a transition. But there's not quite obvious this kind of latent state that happened in the high literacy group. Continually, if we come deeper and compare with the high literacy group and the low literacy group with their correct and incorrectness for this specific item, and we find literacy group aimlessly hit a cancel and a redo, And the high literacy group find the key information in spreadsheet, but did not input this information in the environment. So that means when they make some mistakes or make something wrong things to incorrectly solve an item, they will make something different mistakes. And you can see some mistakes that is randomly cancel and redo. But in the other group, the high literacy group, they have some strategy, but they miss some part when they input their responses. And also we find the low literacy group and the high literacy group that use different strategies in correctly solving them. So for example, low literacy group are more likely to use a sorting, and high literacy has a new latent state of sorting. So we can see these figures over here. So for example, in the high literacy group, actually we can find there's one more latent state like a sorting. Sorting actually is a kind of one layer down, because that is not easy. You can find this kind of strategy only based on their only based on their action sequence. And also you can see, compare with the low literacy group and the high literacy group in the incorrect strategy, we find the low literacy group, when they click cancel, they will go back and forth. They will not do other actions, but they just do back and forth and ending. But for the high literacy people, you can see when they cancel, they will go back to the other strategy. They want to find when the hesitative behavior is showing up to say they cancel, and they want to cancel, and they want to find whether there are other supporting evidence or other actions they can use to solve this item. So there's a big difference over here. So for some discussions here, we can find from our preliminary results suggest low literacy adults and high literacy people, they have a different latent states. So that means that they will use a different strategies when solving the same task. And high literacy adults are more likely to use advanced tools that could not be directly seen from the surface. For example, they will use sorting as their strategy. And also low literacy adults show more hesitative behaviors than high literacy adults. And the last one is when we use the HMM model is a feasible approach to extract latent states of the problem-solving process and visualize the transitions among the latent states. And in our future directions, we want to extend our standard HMM model to multi-group HMM by incorporating covariates from background variables, for example, like age, experience in digital tools. And the second is we want to incorporate adults' latent trait, for example, their latent trait from numeracy and literacy into the HMM to better interpret the latent states underlying the problem-solving process. And finally, is we want to support the parsimonious modeling and description of behavior pathways. Finally, we want to acknowledge our research funded by the IES, and also it's very good collaboration with the Georgia State University and the University of Washington. So thank you very much for your attention. This is the end of my presentation, and I'm looking forward to have further discussion with you. Thank you.
Okay, we'll go ahead and get started, and I'll go over I'll keep this in the chat, the directions for anyone who comes late. What we're going to be doing is going in the order of the presentations to address questions. And so if you have a question, if you could put it in the chat and lead with the researcher you're directing the question to, because they may be able to answer the question while someone else is speaking. And so we'll get through as many questions as we can. And Britt sends her apologies for not being able to attend, but please email her any questions. And so you'll see her email in the chat. So go ahead and you can start entering your questions. If you have a question for a specific person, in a minute, we're going to have Shin go first. And while people are entering their questions, I will let you know that my name is Sarah Brazel. I'm the program officer at the National Center for Special Education Research, and I'm the program officer that was over the new competition we had a couple of years ago to use the NAEP process data for grade 8 mathematics 2017 data that Shin and Juanita presented on. And we really are encouraging people to continue to use this data, as well as the grade 4 data that's going to be released soon. And so I will be putting some links into the chat for more information about the grade 4 data that we have right now. And even more information is going to be coming out in preparation for that release. And Also wanted to encourage you, even though that particular competition was specific to students with disabilities, you can use the data for different populations, different questions about math. And so there's just lots of applications. And we also would really like you to let us know at IES some of the data that you are interested in. Like yesterday, it came up in a science networking session that the ECHLS data, they really wanted subscale data for that science assessment. And so if there's other process data you're interested in, I mean, I think we need to hear from the field. And so we would love to, know that kind of information. Okay, those of you who are just coming in, I'll put the directions in the chat. We're looking for questions. We're going to be starting with any questions for Shin. If you could put those into the chat, and then also any other questions for Juanita or Elizabeth, they would be glad to answer any questions you have. And also you're welcome to use the hand feature and raise your hand. Okay, it looks like someone put a question into the question and answer box, which we will address, but if you could please put your questions in the chat, that way everyone can see them and people can respond. So this question is coming from Russell Almond. Is there a standard format for process data? And are there tools for converting between formats? It's a very good question. Let's see. Shin, when we start with you, do you have any response to that question?
Thank you so much for this question. I have experience analyzing the process data for 2017 NAEP 8th grade assessment. For that data set, it could be different from the 4th grade data set or other data sets. So for that particular data set, we had a item level log file. There is also a feature level file. For that feature level file, it was extracted based on the item level log file. So if you want to understand student at the student level and what process was overall process, you would like to use the feature level data. But if you want to drill down at each item level, like what I presented in this presentation, what was the first action, what was the associated timestamp, you would need to go to that particular data set. My impression is the 8th grade data set is a little harder to use than the 4th grade data set. The upcoming new data set that will be released will be a lot better that in terms of data structure and everything, but I haven't seen that data set either. So I would hope get more information from Sarah and the NCES in the future.
Yeah, and I think John Whitmer, he's our IES fellow, he's put some great information into the chat. And this was actually a very lengthy conversation we had at IES when the 2017 8th grade data came out about what is the appropriate type of data to release, because we wanted some equity of access in terms of different researchers that could use this data. And so John is correct that XML was the original base format, but we ended up transferring that to this feature data set that she mentioned. So it's going to kind of depend on the choices the provider of the data is making. Juanita, I was going to go to you next. Do you want to say anything more about that? Did you also use that data or?
Yeah, just in terms of accessibility, like John mentioned before, the pre-processing of the data, especially if you have the raw XML, can be painful and kind of lengthy if you're not familiar. And to be honest, the XML structure, even between different subjects, I'm talking specifically about NAEP because that is the data that I work with. The XML structure of math data is not the same as the XML structure of reading data. So if you're familiar with math, you're good to go. But if you've never seen the reading XML structure, it is very different and a lot more complex and complicated. So in terms of presenting the data for secondary users, we pre-process the data for them and then try to figure out what is the best accessible way to give it to the folks. So in the last release for the process data, it was provided as text files, because those are pretty open and anyone can read them in. They were tab delimited text files, and so you could read them in however you wanted in R or whatever way. For the new 8th grade or for the new data set, we are playing with a few options, whether we want to keep tab delimited text, we want to provide other options like R data files or Python files, state files, whatever. So I would also just ask anyone in the chat, if you're familiar with this data and you have a preference, you could all kind of let us know, and then we could take survey while we're here and think about what we would like to do to provide it to you all. That would be useful.
Elizabeth, what about your data set? Do you want to share anything about the format that it came in?
Sure. So I'm working with the PIAC data set, and I sort of mentioned in my presentation that they differentiate between the public use files and the restricted files. And so any of the process data from the public files is readily available and downloadable in, I believe, SAS as well as SPSS. We just read it into R to do our analyses. And similar to, I think, what Shin mentioned, as we've been working with restricted data, Britt is the person who usually handles that. It's item level log files.
Make sure you put some questions into the chat if you have other questions. And this session is actually going to automatically end at 12:45. And we would like you to fill out the survey at the end. We would appreciate that. And I'll go ahead and put the link back in the chat while we have our presenters. Any other questions? I'm going to start putting in some resource links. So it's really great to see that this kind of research is being accepted by our special education journals. And so here's a journal by Shin's team, Journal of Autism. You can take a look at it if you want. Okay, John has a question maybe for Juanita. Have you thought more about how the processes map to problem-solving theory?
Yes, but John, I'll be honest, not much, only because the initial part of the analyses for what I showed was just to see if process mining works in this case. All the previous use cases that we explored in the literature were for things like actual systems, how people use the system. You have a finite set of actions, and if the people or the users of the system fit how we've designed the system in the first place. Not exploring something as flexible as an item in NAEP where students could do anything. So we wanted to test the model just specifically for that. Does it actually reflect student processes in a way that makes sense for how they answer the item? Because to be honest, we weren't sure with all the flexibility that it would even show us something that was useful, that we think we know to be true, but we could not explore without something like this. Now that the first question has been answered, we want to continue to do more with the conformance checking, which I didn't talk about in here, which is more related to the problem-solving theory. So how what we see in the process mining or the discovery models relate to the specifications, for example, that test developers have when they design items, and the hypotheses that subject matter experts have when they think about how students are supposed to respond to these items, to see if what we actually see from students align with either one of those, which was great, or not, in which case those individual groups might want to hear some of the things that they have either not identified or maybe looked over that you just see in real life that you don't see when you are theorizing something to be done. Does that help or answer your question just a little bit, John?
And John, you can unmute. Yeah, go ahead.
Okay, great. Yeah, just it does answer my question. Have the same aspiration. Wouldn't it be nice if people designing the framework and items could intentionally instrument those items so that we could see that in the end, rather than, I call it, picking the pieces up that fell off the back of a truck and trying to reconstruct the latent constructs, right? That so I think that's an area, and I know that's something that NAEP is currently exploring as well in the building of the eNAEP. Great.
Yes. Yeah, and the next gen eNAEP, I think they've taken all the years of research that we've done to help the next generation platform. And I would be really interested to see how the new platform then aligns with some of the stuff we're doing now, to see if those changes have actually occurred and that we can observe them.
That integration of the item development all the way through the instrumentation is kind of a long design process. Interesting. I don't know what to see how that's done there, as well as at other assessment systems. Exciting to see. Imagine if we could instrument for disability theory and other ideas that we have, so we could more readily observe that. Would make our work a lot more.
They're about to shut us down. So there are 2 comments in the chat in case one of them looks at it before we shut this down.
I'll just say for anyone, please email us your questions. If you didn't get a chance to ask them here back in the recording, we'd love to respond to them since we're shutting down. But thank you everyone for joining.